We can write the shear as the other possible second derivative, like so. Now, what could we do beyond that? Well, first of all, we could notice that shear varies from place to place. If we were doing galaxy-galaxy lensing, then we'd be familiar with having a foreground galaxy which is red, with background galaxies in blue there. Let's take those three galaxies, put them to one side, and examine what would happen if we glued them together. You notice that immediately we get an arc. So, if we look at the gradient of shear over position, then that gives us an arcing which we can understand as flexion. If we want to write that down mathematically, it's going to be like this. We simply take the next derivative of the lensing potential, which we clearly can see is then simply the gradient of the convergence. This is what flexion actually looks like. It is beginning to look like a skewed object if the initial object was a circular Gaussian. So a few things to notice about this one flexion. First of all, it's a vector. You have to rotate this by 360 degrees to get back to where you started. Bananas are vectors. I'll leave you to think about that. The other thing about this one flexion is that it's local. If we measure the flexion of an object, that is the gradient of kappa at that object, whereas shear is not related locally to the density. Just to emphasize, this is the gradient of the projected matter density, and it quickly dies off away from a halo, whereas a long way from a halo, the shear can still be significant. This dies off much more rapidly, so we could understand it as a high-pass filter for density fluctuations. You'll see that more clearly when I get to power spectra. But that's not the whole story for flexion, because there is another third derivative we could take. Instead of d star dd psi, we can take ddd psi, and that is a spin 3 quantity. Every time we take a d, that is raising the spin by 1. Every time we take a d star, that lowers the spin by 1. So G is a 3-spin object. It looks like this, if the initial object was a circular Gaussian. The important thing here is that this is now back to being non-locally connected to the density field. So now we can say what an arc is. In the weak lensing regime, it's simply a shared object plus a little bit of the one flexion plus a little bit of the 3 flexion. So back to theta prime equals a theta. What does this do? How can we write this? We're just adding a term in a Taylor series, taking this now to second order in image or source positions. And what is this D matrix? It's not entirely pretty, but it's not awful either. This is now an 8-component object, and it's a sum of 2 different terms, one involving the 1 flexion and one involving the 3 flexion. So it all separates out quite nicely. And the question is, how can we measure this, and is it an interesting measurement when we get there? So how do we measure it? Well, Akura et al.'s approach with holics, which are higher order moments of the light distribution, are very promising, but instead we've been using shapelets. The idea of shapelets, which has been mentioned already today, is that we decompose a galaxy into a certain amount of a Gaussian plus a certain amount of a Gaussian times a Hermite polynomial plus ... And we can find what these certain amounts are by taking the dot product of the shapelet in question with the galaxy we want to know the A of. So we want to measure Aij for all of the objects, and then we can make estimators of both the shear and the flexion from the Aij's we measure. So how do we work out those estimators? Well, imagine you've got a circular Gaussian object. These are the different polar shapelets that any object could be decomposed into. If you like, this is the number of radial nodes and this is the number of azimuthal nodes of the relevant shapelet. So if we start with a circular Gaussian, what does shear do? Shear moves power to these components. These are spin 2 components, and as you can see, a Gaussian plus a little bit of something like that will give you an elliptical object, as you might expect. All of that can be written in terms of these ladder operators. So you simply operate on a Gaussian with these ladder operators, and that pushes things over to those spin 2 components. So working backwards, if you see some spin 2 component, you can figure out an estimator as to what shear would have got you there from a circular Gaussian. So you construct estimators associated with these different amounts of shapelet coefficients. What does flexion do on this diagram? The one flexion takes you from a circular Gaussian to things with spin 1 components, as you might expect. It's creating skewness. And the 3 flexion gives you some spin 3 components. And again, you can work out all of your estimators from the ladder operators for those operations. Right, so now we're going to get to actually measuring flexion. We have been looking at the GEMS and stages HST mosaics, 30 by 30 arc minute HST mosaics with about 60 galaxies per square arc minute that we're using. The pipeline generically is rather similar to what everybody has to worry about. We detect the galaxies and stars, we use Sextractor. We decompose the stars initially into shapelets, and then we interpolate each of those stellar shapelets across the field to where the galaxies actually lie, and then we decompose the galaxies into shapelets, including deconvolution of those stellar shapelet pieces of information. And then we use the estimators associated with ladder operators to get shear and flexion. So the sort of thing we'd get for all of the stages galaxies, we'll measure a certain shapelet coefficient versus another. We get a cloud, often they have peculiar shapes. And using those estimators, we get the stages flexion catalogue. This is the histogram of flexions in stages. The solid line is the 1 flexion. The dotted line, which is almost exactly underneath it, is the 3 flexion. So they have similar distributions, and the thing you'll immediately notice is that their distribution is much more peaked and much more wingy than a typical shear distribution. So it's absolutely necessary to clip, or maybe we could do something cleverer, but at the minute we're clipping, we clip such that the flexion is less than 1 per arc second, and then we find that the flexion standard deviation we're looking at is 0.1 per arc second, so 10% per arc second. So, what can we do once we've measured these flexions? Well, we could look at galaxy-galaxy flexion. So, just like I was showing earlier with shears around a foreground object, here we have flexed bananas around a foreground object. Barney has done a careful maximum likelihood approach to this problem to look at the mass of a typical galaxy and the concentration of a particular galaxy in the GEMS data. But this is a more straightforward estimate of the tangential shear and radial flexion around foreground galaxies. This is the sort of thing you're used to with a shear, a mean shear in bins around foreground galaxies. It fits nicely to a 10 to the 12 solar mass galaxy. The best fit there is the black line that goes through the points. Now let's look at the flexion information. This is on a much smaller scale. This is now up to 10 arc seconds rather than 60 arc seconds. And we find that the flexion signal is only rising up on the 2 to 4 arc second level. The black line, which is the same model as above, fits the data rather well although, it's the other way around, I'm sorry. The dashed line is the best fit up there. The dashed line here is the same model. You can see that it doesn't really fit these 2 points particularly well. The black line is the one that goes through the flexion points. That's the best fit to the flexion, which fits the shear reasonably, but is not the best fit to the shear. So there is some tension there. If we turn that into a maximum likelihood estimate, you can see that tension for yourself. This is a measure of the velocity dispersion of the objects. This is the scaling with luminosity, and we find that there is a different velocity dispersion favoured for shear and flexion at the moment. Why is that? Well,
which is which?
that is flexion, that is shear. And because of the way that the chi-squareds look around here, the black, which is the combined, is very close to the shear at the moment.
The inner contour 68 and
Yeah, 68, 1, 2 and 3 sigma, yeah. Okay, so what does this tell us? Well, first of all, it may be that we're beginning to probe into a region where you really should include baryonic physics, so that may account for some of the issue. Another thing is, maybe we haven't calibrated properly. It's the story of our lives. So just like STEP, we need a FLEXION implementation program.
What's the profile you're looking for?
Oh, right. In this example I gave here, that is an SIS, but Barney's also done NFW things as well.
This is vector flexion, not
This is one flexion. Yeah.
well, it's the whatever you want to call the radial component of VF. You're not
That's
including
right. Yeah. This doesn't include G. Some of Barney's plots I could show you afterwards include G also. G turns out to be it doesn't have an impact on this plot, but I'll show you that later.
significances.
Yeah. So we need a flexion implementation program. Richard Massey has helped us with space step type simulations, and we're measuring input flexions versus output flexions. I don't want to tell you what the result is yet because we're very near to a result and I wouldn't want to tell you the incorrect answer. But early indications show that the amount of multiplicative error is going to be less than 10%, but nothing promised yet. So, assuming that we can sort out these systematics, these multiplicative concerns, or understand the physics that would need to go into it to make the model better, then we could look at what sort of accuracies we would get for a measure of mass versus concentration for galaxies in the future. Here's an example where we've calculated it for 1700 square degrees. And what we find, the dotted lines are the shear constraints, the dashed lines are the flexion constraints, and you can see that the flexion is not adding much to our knowledge of the mass, the typical mass of the halo, whereas it does improve the concentration by about 40%. So it is interesting to include, and of course it's an important test of systematics as well. There's another thing you can do in a galaxy-galaxy lensing context that I'm quite excited about, but this needs an awful lot more work. And that's the idea of looking at the excess variance of the flexion in annuli around the galaxies. With a high-resolution simulation of galaxies from the Zurich group, I've looked at the mean flexion in annuli around these galaxies versus the variance, or the standard deviation of flexion in annuli. The dashed line is the standard deviation of flexion, and you see that it's actually a stronger signal on many scales than the mean flexion, and this is telling you about all the substructure clumps around the galaxy. We've tried this out on the stages data, and we are already seeing below 20 arc seconds an interesting excess variance in these bins, which may indeed be the first example of this, but this needs some more work. If this holds up, then it'll be an interesting way of looking at substructure around galaxies. This straight line is the 1 sigma in 1 arcsecond bins, so that you can see that every single 1 arcsecond bin will have a very strong flexion variance signal with both DES and even more so with Euclid. And of course this will be sensitive to different gravities, but it will be also very sensitive to the astrophysics of what's going on in the baryonic region. So an awful lot of work has to be done to interpret the results we get.
Does electricity matter at all here?
Haven't tried the electricity yet.
Because that might also give you an excess.
Yeah, that's right. If you look at the excesses that you expect simply from kappa raising and lowering, it's about a factor of 10 less than the fluctuations you expect simply from substructure, which is really interesting. But you may want to rotate your objects first to get rid of that. Okay, so that's the state of play with galaxy-galaxy flexion, but you can also look at flexion power spectra or flexion correlation functions. Here's the typical shear power spectrum in slightly funny units. If we compare that with the flexion power spectrum, we find that this power spectrum is effectively, to a pretty good approximation, L squared times this power spectrum. In other words, it's weighted towards small scale power. It's weighted towards substructure. If you look at the correlation functions we're actually finding with stages, there's 2 important points here. First of all, there's no detection yet of the cosmic flexion. Secondly, aren't the systematics under control extraordinarily? We're not getting spurious big flexion correlations here. It's all good to within 1% of 0. If we look at what we expect from the power spectra I showed on the previous slide, we expect to get on this plot a flexion correlation of 10 to the minus 5 on 2 arcseconds, which is about the size of that inner error bar. So at the minute we're at the 1 sigma level without a detection, but it is consistent with extrapolated lambda CDM with sigma rate of 0.9, and we're not finding more power than that. So if the systematics continue to be under control, what sort of signal would we expect in the future? Well, this is the signal to noise for a 100 square degree survey. The errors would be 50 times smaller than this for DES, so we would be getting to extraordinarily small flexion variances, which will be a rich source of information about halos. I wouldn't want to interpret this in terms of cosmological parameters, but rather the astrophysics of those halos, really. We can also think about mapping. You can do a Kaiser-Squires inversion of shear. You can also do a Kaiser-Squires type inversion of flexion. And whereas the shear errors in the Kaiser-Squires inversion are formally infinite, so you have to smooth, that's not so for flexion. So here's a smoothed shear map, taking the same kappa variance effectively per pixel for the flexion map and adding it, we find that we get this. So you begin to see much more detail in the shear plus flexion kappa maps, which is very exciting. A lot of these structures do appear to be real, or at least correlated with galaxy numbers. And importantly, there's 126 sigma correlation between the flexion and shear maps. So flexion measures the same thing as shear, which is good in terms of dark matter kappa. So now on to something a bit more fun. There are more image distortions than we've talked about to third order. Have a look at A again, and you'll see that although there are 4 possible numbers in a 2x2 matrix, we've only got 3 numbers there, kappa, gamma 1 and gamma 2. There is another mode that can be achieved in A, and you know what it is. It's the rotation. You can get rotations, and indeed they're seen in B modes of our shear signals. And the key thing about theta is that it can't be written as a derivative of a scalar potential, Whereas we wrote kappa as d star d psi, we wrote this as d d psi. Can't do the same with theta.
I think you can, but the potentials are complex.
Okay, I take it back. A scalar real potential. Yeah. Dijk, which is the next level, has 4 unused degrees of freedom. Remember, there were 8 things in that object, and we've only used 4 of them. 2 components of 1 flexion, 2 components of 3 flexions. So what are the others? Well, after quite a bit of effort, they're what we already knew. There are 2 further terms. There's something here, which has a rather simple form, and there's something here which looks more complicated. Let's start with the more complicated one, because it's more exciting. T is what I would call the twist, and this is what it looks like. That's taking an elliptical object. How does T operate on an elliptical object? It creates an aerofoil, really, an unsymmetric object which is twisted. And if you like, this is almost like gluing together some objects in a B mode, for those of you who think in those terms. C is the gradient of the rotation. So that seems to me to be suitable to call turn. And this is what it looks like on an elliptical object. It creates a gradient of rotation across an object, indeed rotates the object into an arc. So again, it looks like the flexions, but it really is a different mode. It looks like F and G, but whereas F and G on a circular object give you something non-circular, C on a circular object has no effect, because a differential rotation on a circular object creates a circular object. So what do twist and turn do on the shapelet states? What's really interesting is nothing changes from a circular Gaussian. Nothing changes from any circular object. It doesn't operate. It only operates on objects which already have an ellipticity. That's what twist does. It moves things from the spin 2 components into various spin 1 and spin 3 components. And this is what the turn does. It moves things again, but into slightly different components. So it's really quite interesting. Can we measure it? Well, we've tried. It turns out that it's got a much larger variance than the other distortions that we've looked at. But even on quarter of a square degree, we're already getting something quite interesting. The mean twist in the stages survey is 0.02 per arc second, so that's already at shear type levels. And the turn, again, similar sort of variance, slightly more than 1 sigma. Is this a systematic? And of course that's the question which we would use twist and turn for. We don't expect a strong gravitational twist or turn, but they will be very important, just like the B modes in shear, for looking at systematics. So for DES, T and C will be measured to within 10 to the minus 3, which will be a very important test of the systematics in those surveys. So the summary is that flexion we can now measure, and it has lots of potential for small-scale mass. Galaxy-galaxy flexion can improve our measurements of concentration, and via this variance, hopefully improve our understanding of halo substructure. Cosmic flexion will constrain substructure, but it's still a bit too small to measure so far. We can improve the resolution of dark matter maps with our approach. And twist and turn will measure systematics. And at last, that's the lot of distortions to second or third order. So thank you.
All right, questions? Yes?
Have you tried to measure flexion on 86 and 89?
Okura et al. Have, and they've done a brilliant job. I'm sorry I didn't show that result really, but I can show you afterwards. What's really interesting is that they find sub-peaks, which you don't find with shear maps typically.
So do you do a better job of constraining the mass if you use both shear and flexion?
Yeah. I mean, on scales where both shear and flexion can look, then you're adding to the signal to noise. But on these really small scales, you're genuinely adding information that SHEAR couldn't see.
Yes, Phil?
Can I see a very large spike in the cosmic reflection?
Yeah. So I don't believe that. Why should we believe that? That's sort of that's the 0, 0. That's very, very close. So it's going to be very.
Expect the power to be high. Isn't that when the signal is predicted to be high?
Oh yeah, but I mean, you know, on a 1 arcsecond scale, you've got horrible overlapping isotopes. The miracle to me is that it doesn't contaminate further out, actually.
A related question, so a sky gradient is a vector signal too.
Mm-hmm.
Have you checked to see what level of sky gradient would produce the F signal that you saw?
No, that's a very good point. Let's have a look.
So
Yeah.
you expect a sky gradient in the vicinity of galaxy.
Yeah. And again, my point is the same again. It's quite remarkable. I'm very surprised that we're getting such a low signal here. You know, it's within cosmological expectation rather than what I would have expected, which is bad luminosity systematics.
Yeah, last question.
One of the complaints of shapeless is that it has problems of measuring extended objects. So how does it perform on these banana-like structures?
Sorry, can you repeat the question?
Well, one of the complaints of shapelets is that it has problems to make reliable decompositions
Yeah.
of extended structures.
Mm.
So how does that work for like bananas?
Yeah. I'm not quite sure how to answer the question. I mean, it's clearly going to be a concern, and one of the answers will be the full results of FLEP, to tell the truth. You know, let's see how well we can do.
I suggest to break here for coffee, so we can start again in 15 minutes. And let's thank David again.